Okay, this video is on graphing polynomials using end behavior and multiplicity, so without using a calculator. First thing we need to do is just make sure we understand what end behavior and multiplicity are. So the end behavior of a polynomial is basically talking about the direction that a graph is pointing in at the left and right ends. So for instance, let's see here, black. So if I have a graph and it looks something like, I don't know, this, and I'm talking about end behavior, all I really care about is what this arrow and what this arrow are doing. So this is my left end behavior. This is what's happening as my x values head towards negative infinity. And this side over here, end behavior, is what's happening as my x values head towards positive infinity. What their answers to the end behavior is that y could be either heading up towards positive infinity or y could be heading down towards negative infinity. It's a little notation issue here. So what ends up happening if you examine enough of these all together, some patterns emerge. So if I look at my polynomial and I see that the lead coefficient, remember that's the number at the very front if I'm in standard form, if it's positive and that the degree of my polynomial is even, then the ends of my graph on the left is always going to be going up and on the right will always be going up. So if you're ever stuck, you're thinking here, like for instance, this is like x squared. We all know what x squared looks like. That's a positive lead coefficient, an even degree, so its ends would kind of show us what happened. If I have an even degree, but now the number out in front is negative, this is like the idea of like negative x squared as a point of reference. So think about what the ends of that look like. We know it opens down, which means that both the left and the right hand ends are going down. So that would be down, down. Now I can talk about what happens if my number out in front is positive, but my degree is odd, so 1, 3, 5, 7, etc. And if that is going on, then my left end will be pointing down, and my right end will be pointing up, so down, up. If I have a lead coefficient that's negative and I have an odd degree as well, it actually will look like this graph over here. On the left, it'll be pointing up, and on the right, it'll be pointing down. The even ones are pretty easy to remember just because we can refer back to what's happening with x squared and negative x squared. We don't really have a long history of an odd degree polynomial. X cubed would be the easiest one. Actually, that's not true at all. I don't know why I just said that. The easiest one that you can think of is x. Y equals x. That's degree 1. We know that that's a line with a positive slope. So there's the left end pointing down and the right end pointing up. And this would be y equals negative x, so this would be a line with a negative slope, so it would be going like this way. So left end up, right end down. So that's probably the best point of reference. If you don't want to memorize, you can just always think about what these four most basic even and odd degree functions look like. Now, when we're talking about this again, I'm saying that we have a polynomial that's given to us, right? So we have some equation, I don't know, maybe it's this. So this is odd, negative, so it would be odd, negative, so it will go up, down. I need to have the polynomial in order to be able to answer this question. Obviously, if I have the graph, I already know the answer. But most of the time when we are working with these, we are going to be in factored form. So factored form for a polynomial says that my graph, or my equation, excuse me, will be something more like this. Either we factored it ourselves, which we will do later in the unit, or it's just given to us. When I'm in factored form, the question is how do I figure out the degree? I can multiply it all into standard form, which would be really time-consuming and unnecessary, or I can add the degrees of each of the factors. So if I look here, I have 1, 1, and 2. So this guy is degree 1 plus 1 plus 2. Or 4. So this guy would be even, and then lead coefficient is positive 1, so be even positive. So this guy would have to go up, up. Okay, so that's the first piece. The second piece has to do with the word multiplicity. We've never seen this word before. So multiplicity is how many times a factor or 0 is present in a polynomial. So I have to be in factored form. The multiplicity is super important because it's going to tell us how the graph looks when I'm focusing on that one particular zero. So I'm basically cutting my graph up into a bunch of smaller pieces, focusing on the ends and then on each one of the individual x-intercepts, and then trying to put all those pieces together. If a factor has a multiplicity of 1, that might be if it looks something like, I don't know, it's y equals x to the first, or maybe it's just a factor like x plus 2 and there's no exponent outside of it. We say that the behavior, what it does at that 0, is it crosses through, or just crosses at that 0. It's degree 1, this factor. That means it's going to look like a line. That's why it's just going to cross through. So if I have an x-intercept over here and it had degree 1, I'm going to know that it's just going to cross through in a straight way. I have degree 2, that means my factor looks something like, I don't know, this. So that 2 is telling me it's multiplicity 2. We know x squared, this is a quadratic, so this is going to be like a curve. That makes sense. This guy would be over here, and we're going to say that it it bounces. That's how we're going to describe it. Okay, this is like that quadratic, that parabola that's just has one solution. That solution is at positive 1. So in my example that I gave you, that's there. Over here, that would be negative 2. So we say it bounces. That means it looks like a parabola at that particular x-intercept. Our last possibility is that we have multiplicity 3. So let's say, I don't know, x plus 3 cubed. So this 3 means it's multiplicity 3. When it's multiplicity 3, we say that it curves through. We spend a little more time investigating x cubed. This might make a little bit more sense. But what curves through looks like, let's say this is over here at negative 3. I'm going to go from the other direction. Curves through means as it starts to approach it, it's going to then kind of flatten out as it goes through and then continue on its merry way. So instead of going straight through or bouncing off, it starts to look like it's going to bounce, and then it switches the direction of its turn, curves. So I need to know these things along with end behavior, and if I do, then I can put all the pieces together. So let's take a look. I want us to sketch a graph that has the end behavior, the right zeros, the x-intercepts, and that works the same way as it did when we had quadratics, the right multiplicity, and the right y-intercept. So I'm just going to kind of try to make some notes to myself. First, the lead coefficient here, there's a 1 out in front, so it's positive. The degree, it's in factored form, so it's 2, let's see, so it's 2 plus, this guy has a 1 plus 3. So this is degree 6. That's even. So as a result, we can conclude that my ends for positive even go up, right? That looks like x squared. Positive even is up. The next thing we want to talk about has to do with the zeros and the multiplicity. So the zeros we get from looking at opposite the number, so setting this factor equal to 0 and solving. So I have one at negative 2, comma 0. That's my x-intercept. So the x0 is at negative 2. I have another one at positive 1, and then I have another one at positive 4. The multiplicity for each of those zeros has to do with the exponent. So for the negative 2, it has multiplicity 2. For 1, it has multiplicity 1. And for 4, it has multiplicity 3. I'm just trying to make sure I have one of each there so I can show you everything in the example. They could all have multiplicity 2. They could all have multiplicity 1. So I just have all 3 because I wanted to illustrate what that looks like for each different one. The last thing we want to think about is how is it going to behave. So multiplicity 2 means it's going to bounce, right? It's going to go like this. Multiplicity 1 means it's going to cross straight through like that. Multiplicity 3 means it's going to curve like that. I want to put all those things together. Ooh, a y-intercept. For the y-intercept, I need to focus on the numbers here only. So I want to do 2 squared times -1, times -4 cubed. I picked terrible numbers here for that. Negative cubed is negative. 4 times 4 is 16 times 4 is 64. So I have a y-intercept that is at positive 256. You're certainly not doing anything to scale, so I'll just throw that label on there when we get there. All right, sketch. Here we go. Are you ready? I need to first note my end behavior. Up, up. I'm going to draw that on before I do anything else. Next, I need to put on my zeros. I have no scale here, so I'm totally creating it myself. So I'm going to say that this is -2. Positive 1, I'm going to say, is around here. And then positive 4, therefore, will be somewhere around here. Okay, work left to right now. I'm starting from pointing up. When I hit -2, I have to bounce. So here comes my graph. I'm going to use a different color here because this is way too far over. So I'm going to come towards -2 and I'm going to start to curve. And as I hit the x-axis, I'm going to turn. So I've bounced at that 0. Next, when I'm hitting 1, I need to cross straight through. It actually winds up, I'm going to be coming downwards because I'm heading up already. So I'm going to be actually going this direction. So I'm going to go up for a while because this is supposed to be my y-intercept. I'm going to turn around because I have to turn around in order to be able to cross through this. And I'm going to say, I don't know, go something like that. I don't really know how high up it goes. I don't really know how narrow or fat this is, but this is pretty good. Last thing, I have to hit 4. When I do, I have to curve. So to not make it too squished, I'm going to continue to go down. In order to get to 4, I have to turn around. So I've created a minimum for my graph. As I head up towards the 4, I'm going to flatten out. As I hit it, I'm going to change the direction of my curve, heading upward. So I have the 2 arrows pointing up. It bounces here. It goes crossing straight through there, and it curves through here. Last thing I'm going to do to make my teacher happy, I'm going to quickly go back and relabel these so you can see them. That's 4, and they wanted the y-intercept labeled. We said that that was at 256. Done. That is my sketch. Okay, one more example. X cubed times x minus 5 squared. So again, I'm thinking lead coefficient, positive, degree, 3 plus 2, which is 5. So I have positive, odd. So my ends have to go down, up. Okay, my zeros, x cubed gives me a 0 at 0. X minus 5 gives me 0 at 5. The multiplicity, x cubed is 3. X minus 5 is squared, so it's degree 2. Last is behavior. If I'm degree, then I'm 3, then I'm going to curve through. If I'm degree 2, I'm going to bounce. I'm ready for, oh, I didn't do my y-intercept. I always want to forget that y-intercept. Y-intercept says when x is 0. So let's see, f of 0 is 0 cubed times -5 squared. That 0 times anything is 0. So my y-intercept is 0, 0. That's convenient. That makes sense because I have a 0 at 0. All right, sketch. Ends, down, up, down, up. Zeros, 0, 5. Okay, I'm ready to graph. Y-intercept 0, 0. Perfect. So I want to start from downwards, and as I hit this, I'm going to curve through it. So I'm starting from down, I'm going to come up, I'm going to flatten out, curve through. Arrow there. I need to hit 5, but I'm heading up, so if I keep going up, I can't ever hit it. So that means I need to turn around. So turn around, and when it hits 5, it needs to bounce. Come down, touch curve into 5, and bounce. Arrow up. Done. That is it. That is my graph. Correct ends, correct behavior at the intercepts. I don't know how tall this is, and that doesn't matter for our purposes right now. In order to figure this out, you would need a graphing calculator, and that would be on a different section of an assessment having to do with graphing polynomials.